Okay, today we're talking about another goodness of fit test. This is the one that is going to follow a distribution. So it's still used for categorical data, but it's for items that we do not think are equally distributed. So they follow some distribution. So the null hypothesis is exactly that. The distribution is as stated. So basically nothing's changing about what we believe to be true about a particular distribution. And then the alternative hypothesis is that the distribution is different than stated. So not all of the values need to change, but at least one of those values is different than the hypothesized distribution. We find expected values a little bit differently. Instead of just taking the total and dividing by the number of categories, we're going to multiply the total by each percentage. So if there's supposed to be 20% of a particular category, then we're going to multiply 0.2 times the total sampled. All other steps pretty much stay the same as the goodness of fit test that we talked about yesterday for equal frequencies. Okay, so here's our first example. It states Acme Toy Company prints baseball cards. The company claims that 30% of the cards are rookies, 60% veterans, and 10% are all-stars. The cards are sold in packages of 100. Suppose a randomly selected package of cards has 50 rookies, 45 veterans, and 5 all-stars. Is this consistent with Acme's claim? Use a 0.05 level of significance. Okay, so first of all, our null hypothesis is that the percentage are as stated. So 30% of the cards are rookies, 60% are veterans, and 10% are all-stars. So the distribution is as stated. The alternative hypothesis is that at least one of those percentages are changing. So the distribution is different than what is stated. So the distribution is different than stated. Sorry, my handwriting is so terrible on this Chromebook, guys. Okay, so that's step number 1. Step number 2, we're still going to find a critical value. It is still on the chi-squared chart. And again, the area that indicates that the distribution would be changing is where the observed values are really different than the expected. So that's that right tail of the chi-squared distribution. Okay, our degree of freedom are the number of categories minus 1. So we have rookies, veterans, and all-stars. So we have 3 categories minus 1. So we have 2 degrees of freedom. And it did say to use an alpha value of 0.05 in the prompt. Remember, guys, if it does not state an alpha value, 0.05 is the commonly used and therefore the default. Okay, so let's take a look at the chi-squared chart and see what that critical value is for 2 degrees of freedom and an alpha level of 0.05. So here's my 0.05 column and 2 degrees of freedom. It looks like that number is 5.991 right here in the chart. Okay, so 5.991 is our critical value. Okay, step number 3 is our formula, and it's still the same as yesterday. So chi-squared is equal to the summation of the observed minus the expected difference squared over expected. Again, you would do this for every single category in the data. So we only have 3 for this example, so we're going to go ahead and calculate that. Before I do that, I'm going to clear this slide so we have some room. Okay, so first of all, the observed values are given in the prompt. We have 50 rookies, 45 veterans, and 5 all-stars. So those are the observed values. I'm just going to write them here beside O. 50, 45, and 5. But to find the expected values, I need to figure out, well, what is 30% of the total? What is 60% of the total? And what is 10% of the total? This one's kind of easy because the total's 100. So if I take 0.3 times 100, I'm going to get 30. So my expected value would be 30 for rookies. 60% of 100, again, 0.6 times 100 would give me 60. And then 0.1 times 100, that would give me 10. So my expected values are 30, 60, and 10. Okay, so doing that formula, the first observed value is 50 minus its expected value of 30 squared over 30. We're going to add that on to the next one. The observed value is 45 minus the expected value of 60 squared over the expected of 60. We have one last one left. So the last observed value is 5 minus the expected is 10 squared over the expected, which is 10. Okay, guys, I could plug and chug that formula, but I'm going to go ahead and use the calculator to calculate this. So I'm going to go to Stat and Edit. Just like yesterday, I'm going to put the observed values in list 1 and the expected values in list 2. Okay, I went ahead and put those observed values in list 1 and the expecteds in list 2. I'm going to go to Stat, over to Tests, and I'm looking for, again, the chi-squared GOF, goodness of fit test. The calculator is just going to remind me, make sure your observed values are in list 1, your expecteds are in list 2. I do have to put in the degree of freedom, which remember we said earlier was 3 categories minus 1 or 2, and then calculate. So the calculator tells me that that chi-squared test statistic value comes out to 19.583. That was all step number 3. Step number 4, the p-value, is in scientific notation here, guys. Make sure 5.59 is not a valid p-value. It is, the p-value represents a probability, so it needs to be between 0 and 1. So without saying times 10 to the negative 5, it is incorrect to put the p-value as 5.59. Really, we need to move that decimal place 5 spots to the left. So it's extremely tiny, 0.00004 zeros before that 559. So P is less than alpha. Okay, so our probability is low. That is when we reject the hoe. Okay, so my decision, I'm going to squeeze it up here, is to reject the null hypothesis. And then we still have to write those summary statements. So at alpha equal to 0.05, there does seem to be evidence to say the distribution is different than the company claims. Okay, here is another example. Why don't you guys try this one? So read through it, see if you can go through those 6 steps for the chi-squared goodness of fit test for when it follows a distribution, and then unpause the video to get the solution. Okay, guys, hopefully you paused the video and now you're coming back to check. The hoe and the ha stayed the same as it did for the last example. The null, the distribution is as stated, and the alternative, the distribution is different than stated. Step number 2, that critical value is 9.488. That was 4 degrees of freedom with an alpha of 0.05. There was none stated in the prompt, so again, we just use that default 0.05 alpha level. The chi-squared test statistic comes out to 4.62. We can see I used the calculator function to find that. Step number 4, the p-value is 0.3287. That p-value is bigger than 0.05, so it is not low, so we do not reject the hoe. And the summary statement, at alpha equal to 0.05, the distribution that Watson claims does seem to be accurate. So there's not enough evidence to dispute the distribution that she's claiming with her grades. Okay, I just want to go into how we find those expected values for this example, because when we add up the total sampled, it's 63. There's 63 grades from Watson's class. So we do have to multiply the percentages times that total to find the expecteds. So the observed are given in the prompt. Again, those were 8 A's, 7 B's, 28 C's, 11 D's, and 9 F's. The expected value, again, we have to take that sum, 63, and multiply by each percentage. So if I take 0.10 times 63, that gives me 6.3. The next one, the B's, 20% are supposed to be B's, so 20% of 63, that gives me 12.6. And then for the C's, we would need to take 40% of 63, so 0.4 times 63, that gives me 25.2. And then we're back to 20%. So we already did 20% of 63. That was 12.6. And again, 10% of the 63, we did that for the A's, but it's the same for the F's. So that gives me an expected value of 6.3. So guys, I'm showing my screen over here, the calculator screen. I put the observed values in list 1 and those expected values that we just calculated in list 2. And then again, the calculator function, you go to stat, over to tests, and you're looking for the chi-squared GOF, goodness of fit test. Okay guys, hopefully that's making sense. If you have any questions, drop them in our discussion board. That's the lesson for today.